We have the other speaker here, Mr. T.P. Straatsma, right?
Mm-hmm.
Okay, and he's from Oak Ridge National Lab, and he's going to be giving, he's going to be presenting about the #1 supercomputer, the summit. Welcome, Straatsma.
Sure. So just like Rob, I'm in the application area. I've been responsible for the application readiness for Summit for the last 4 or 5 years. This is a long process for us to get applications ready. And to follow on the last question that Rob answered about how did you get to the decision to pick 4? And he said we still have a number of codes that will rely heavily on the CPU. And so they opted for a solution that has, in terms of the capabilities, more CPU than we have with 6 GPUs per node. We made this transition from a CPU-based architecture to an accelerated Nvidia GPU-based system 5 years ago with Titan. So we have had a little bit more experience than Livermore in what it takes to bring applications from a CPU world into an accelerated GPU world when it comes to these HPC, really big systems. When we made that transition from Titan, or from Jaguar to Titan, that was our first large-scale system that contained GPUs. There was a lot of anxiety about doing that for a leadership compute facility. But we stuck with it, and we got through it, and we believe we made the right decision. So first of all, what is a leadership computing facility? And this really started when the Japanese built the Earth simulator in 1990, late 90s. And so this really shook the world in terms of the high-performance computing, and the Department of Energy was identified as the best agency within the U.S. government to build the next generation of high-performance computing, to really show leadership within the computing world, being for the United States. So with that, it's not as smooth as Rob's talk. Out of that came the concept of the leadership computing facility. This is a facility that has 2 sites. There is one at Oak Ridge, which is the Oak Ridge Leadership Computing Facility, and there's one at Argonne in Chicago, which is the Argonne Leadership Computing Facility. These are the 2 leadership computing facilities of the Department of Energy out of the Office of Science. There's a 3rd facility at Berkeley called NERSC, which is the mission-driven compute facility for the Department of Energy. Now, in the Congress decided when they ratified this bill that established the leadership computing facility that this has to be available to industry, academia, government agencies, everywhere, not just within the United States. It's not only for U.S. institutions, it's open for everyone. So this is what eventually led to the INSIDE program, and I'll say a little bit more about that. So we run these 2 centers, one at Argonne and one at Oak Ridge. And one of the, which is actually a second argument that Rob could not use when he was asked about how did you get to this 4 GPU versus 2 CPU version. We have, of course, a lot of applications that do not run very well on a GPU. Between the 2 facilities, Argonne and Oak Ridge, we have to have different architectures. We cannot have the same architecture. And this is one of the reasons for that is that we have applications that run better on the CPU-centric machine, and we have applications that run better on the GPU-centric machine. So we can support the entire mission space, scientific mission space, with these two facilities. The second reason is it's also risk mitigation. We built the serial number 0 machine. So in siting these machines, together with all the hardware developments that need to take place, the software development that need to take place, there are always a lot of problems with these machines. And now in the case of Summit, IBM does not have another machine to test their software out on. They don't have it, because we have the very first one. It gets shipped straight from the foundry, almost, not exactly, but almost straight from the foundry to our sites. That's where it is being put together. And so we are part of a partnership with these vendors to make this successful. This is not a machine that you go to Best Buy to purchase. This is what we built together. And so it's a little bit of a risk mitigation as well to have two different machines within these two facilities, because there's always a risk that something doesn't work out. And so that's why we have two of them and two different ones. So at Oak Ridge, since I'm from Oak Ridge, I'm going to focus on what we do at Oak Ridge. We've had a long series, quite a series of machines that have been part of this leadership computing facility, and starting in the early 2000s. Jaguar was the machine that we had before Titan, so that was a 2.5 petaflop machine. Then we actually took all of these cabinets and they're the same as in Titan, so it's really an upgrade in that sense. All the nodes were replaced, but a lot of the infrastructure could be maintained. So this is a Cray machine going to Titan. This was the transition where we went from a CPU-only architecture to a CPU/GPU system. So here's Titan again, 27 petaflops. Now we have Summit on the floor, 200 plus petaflops of compute power. The machine passed acceptance last week. On Thursday at 4:30 in the afternoon.
So that's official now? Official.
Well, it passed the acceptance test, so
okay, very good.
There's still a list of things, right? And we are still in discussion with IBM about what all needs to happen. But the test itself and the most important pieces out of those tests have passed. So we're very happy with that. And so is IBM, and Nvidia, and Mountains. But of course, the machine is barely on the floor, and we start the process of thinking about what we need to do for the next machine. We did not want to call that O21, like A21 for Argonne, and so we came up with the name already, Frontier, but there's nothing I can say about what that machine will look like.
But you have that name?
The way we do this is we have a competition within the lab. We can suggest names, and then our director selects.
We thought that was state of Texas.
So Frontier, that's going to be our exaflop plus machine. So a little bit about our user programs. So we operate this machine, and we provide resources to researchers in four different user programs. The largest one is Insight. This is a program that is open to anyone on the planet. They write a proposal. It is reviewed by a panel of experts within their field. It's a very serious review that is being done. And it also gets a computational readiness review. So there are two reviews. Computational readiness review we do ourselves because we know best what that machine is capable of and how well you're able to use that machine. But there's also a scientific merit review. Based upon those two, the centers, or the LCF, the centers together, decide which projects get time on the machine. And this is for both the Argonne machine and the Oak Ridge machine. We do this together. We pick very large projects. So on the Oak Ridge machine, we typically have in the order of 30 projects in this program. So they get a substantial allocation of compute time. And that is because we want to do big science. Our motto is always, if you cannot do it someplace else, you should come to us. Then you can do it here. Of course, you can turn that around also. If you can do it someplace else, maybe you should do it someplace else. We want really the big science out of this machine. So that's the Insight program. Then the second one is the ALCC program. This is the ASCR Leadership Computing Challenge program. This is for projects that are of interest to the Department of Energy. So DOE itself, the program managers in Germantown decide who is getting time as part of this program. You don't have to be DOE funded per se, but you do need to have a project that is of interest to DOE. So it's typically things that have to do with the production, use, and consequences of the use of energy. Then the ECP is a new user project. This is the exascale computing project. This is a new project where a large number of projects get, this is actually funding that they get, to develop technologies, compute technologies, as well as port application codes to the exascale machine. So this is Frontier, this is not Summit. Of course, there is no Frontier, so they have to work on what we have currently, and so that is Summit for us. So they do get allocations on our machine. And then we have 10% going to what we call the Director's Discretionary Program. This is a program that has different goals. One goal is to help folks that want to propose within Insight or ALCC to do the benchmarking that they need for that proposal. So they get a small allocation so that they can run their benchmarks and put that in their proposal. The second big goal that we have with it is to bring in new researchers and especially new scientific domains into the HPC world. So they may not be ready yet to use GPUs very effectively, but we'd like to help them get in there by giving them access to these very large resources. And then the third one is to support specific DOE mission projects within Oak Ridge National Laboratory. But the first two are really important for external folks that want to write proposals or just want to see what they can do with their application on our machine. We will help them. Here typically we have in the order of somewhere between 100 and 200 projects per year. So these are not large allocations, not nearly as what you get in Insight. So how do we get the requirements for what our machine needs to look like? It looks like we, every 5 years or so, do a series of workshops. And we get domain scientists out of different fields, specifically those that are supported by the Department of Energy, to get together for a day or three to talk about what their computational needs are currently and how they see this change in the future so that we can make an assessment of what our machines need to be capable of doing to support that. And so most recently, in between 2015 and 2017, we had a number of these workshops, and I was on the committee that organized these in high energy physics, fusion energy, biological and environmental research, basic energy sciences, nuclear physics, and then OSCAR itself, advanced scientific computing research. And I also was on the committee 10 years ago when we did this exercise. This is how we get the mission objectives and the corresponding capabilities that we need for computing. What is changing from, let's say, 10 years ago to what we recently did is that data-intensive computing becomes more important. Machine learning, deep learning, AI, these are all things that 10 years ago were not really at the fore when it came to high-performance computing. That is very rapidly changing. In the last couple of years, this is really, really changing. So just looking at the projects that we had over the years that were really focused on machine learning and data-intensive computing. These were primarily within the ALCC sphere and within the director's discretionary, so relatively small projects. Nevertheless, it added up to 220 million core hours on type. So it's not huge, but it's significant still. More recently, when we did our call for proposals for early science on Summit. So this is maybe I should back up a little bit. 4 years ago, I did a call for proposals for projects within the application readiness for scientists project. And out of the 29 proposals, only one had some machine learning component in it. And it was not really convincing. So we worked with a set of other codes, and I'll show them a little bit later. But then it became apparent that there are many more teams that are just waiting to get access to Summit. And they think they have applications that would run very well. So in December of last year, almost a year ago, we did another call for proposals for teams that could demonstrate that they could use Summit very well, that they would also get some time on Summit to do their research. And we got 49 proposals, or letters of intent. And we gave all of those teams access to phase 1 of Summit in January of this year. And they got about 5 months to work on that code, do the benchmarking. They didn't get very large allocations because lots of other things were happening at the same time on that machine. And then they had to write a proposal that was due in June. And we got 29, or around that number, proposals for early science. And amongst those, about 1/3 was in the machine learning, deep learning area. So here are a few of those. Dan Jacobson, if you go, I'll mention his name a little bit later. Patton from most of them were from Oak Ridge, because they're sitting close to us and they know about what this machine can do. All right, so Summit, the new 200 petaflop system, the world's largest, fastest machine. Back in June, they were #1, and just today, again, they were #1. So the Chinese did not beat us this time. The fastest computer for science. And this is a slide that's very, very similar to what Rob showed, but our numbers are slightly different. Actually, we have the same number of Power 9 processors per node, but we have 6 Nvidia GPUs instead of 4. We have well over half a terabyte of memory per node. This is divided between the high bandwidth memory on the GPUs and the DDR on the motherboard. And then, just like Livermore, we have 1,600 gigabytes of non-volatile RAM on the machine as well. So the peak performance is officially 200 petaflops. I think it's actually a little bit more than that if you do the math. And we already saw a peak of 3.3 exaops on the GPUs because of the tensor cores that are on the Qualcomm GPUs. And we'll say a little bit more about that. We have 4,608 nodes, dual rail, full factory, Mellanox EDR network, 250 petabytes of file system space. I have another issue here.
Well, I'm sorry. I don't know why this is popping up. Anyway, I'll fix it later.
So the cabinets are exactly the same as what you saw from Livermore, but ours sits on a concrete slab because these things are extremely heavy, and we still have Titan sitting on our raised floor, and so all of our infrastructure comes from the ceiling. And it used to be if you would walk through a supercomputer, you had a hot aisle, and then a cold aisle, and then a hot aisle, and then a cold aisle. Our system is completely water-cooled, and so we have a water aisle, and an electricity aisle, and water aisle, electricity aisle. Just combining those two things doesn't seem like a very good idea, but it is necessary. So we have all the infrastructure coming from the top. These yellow things are cable trays for the InfiniBand network. And then you can see this is electricity coming down, and then in the next aisle you see all the hoses going up and down for water. And it's warm water cooled. So the IBM, we have 22 cores per chip. So they're made with 24, but in the yield we actually use 22. We have PCI Express 4 on the node. The network between the GPUs and the CPU, the one CPU that's available connected to the 3 GPUs on one side is NVLink 2. And then, well, here are the caches. It's not too important for this conversation. And then we have the 6 Tesla Voltas per node with over 5,000 CUDA cores per node, and then these tensor cores. The tensor cores is something that Nvidia really kept secret for a long time, and it was really far into the project that they let us know that we would get these tensor cores. This is really what makes this a very exciting AI machine, and we will see that. And so this is the 16-bit floating point matrices that you can do the multiply, and then the add to a 16 or 32-bit floating point matrix for a 16 or 32 result matrix. And so this is what makes this machine really, really special. This is a picture of the node itself. So you see the 3 GPUs on this side, 3 GPUs on that side, and here are the 2 CPUs, and all these hoses are providing warm water going in and really hot water coming back out. Now, the memory sits here, and there are some other components. Those are not water cooled. So the cabinets have a rear door heat exchanger that is through water. So the entire system effectively is water cooled, and it should be room neutral.
Livermore was water cooled as well?
The Livermore system works the same way.
Okay.
So going from Titan, where we had one x86 with 32 gigabytes of RAM and a GPU connected with 6 gigabytes of GDDR on a thin straw, PCI Gen 2. We now go to a much more complicated node with the 2 Power 9s with the X bus in between, and then so that divides the 2 NUMA domains with 256 gigs of RAM for each of the CPUs, and then the NVLink that connects the Power 9 with the 3 GPUs on one side, and they're connected to each other with NVLink as well, and of course on both sides. So this is a very, very powerful, heavy architecture. So looking at the differences between Titan and Summit to give an idea of what the increase in performance is, we go from baseline on Titan to 5 to 10 times the performance on applications. And for us, it's always the applications that are important. It's not peak performance, it's not being the number 1 on the list. The number of nodes goes down from 18,000 to 4,600. This is very exciting for a lot of people that the number of nodes is actually going down. The node performance as a result goes up from 1.4 teraflop to 42, or better than 42 teraflops. We have a lot of memory on the node, which for a lot of applications is quite a change. We have non-volatile memory on the node. There are not too many applications that really know how to use this other than burst buffer. 10 petabytes of memory on the node. We go from Cray's Gemini to Mellonar's dual rail full factory EDR. We talked about this, we talked about the file system. And all of this with an increase in power that goes from 9 to about 13. So it's a very modest increase in power that we need to get this increase in computational capabilities. So we prepared our users through this application readiness program called CAR, Center for Accelerated Application Readiness. It's a little bit of play of words because we want the applications to be ready earlier than if we had not worked with them, so it's accelerated, but it's also accelerated because it's already used. So we don't pay those folks. Right? We work with them for 4 years, and we pay them back, so to speak, with an early science project. So they get an allocation on the machine and can do a scientific campaign that will show off what they did to their code, but it will also show early science results on something. We use it to base our training and web-based documentation on. Of course, they had access to other things along the way, Titan, Summit Dev. This was the same system that Rob was talking about, the POWER Prime with 2 Pascal GPUs. And then Summit Phase 1, which was 25% of Summit, and then now Summit itself. And it's really to get early science achievements, transfer the experience of what it takes to do the porting of these codes, and get the lessons learned and the gotchas that we can use to help others to do the same thing. Demonstrate the application readiness, prepare people for Insight and ALCC, and then last but not least, harden the system both from the hardware perspective as well as the software perspective, the software stack, to really test that at scale with actual science that we would do on the full machine. So these are the main goals of the CAR, porting these applications, demonstrate early science, get the experience for future users, do the software development testing and the hardware hardening. And we don't do this just by ourselves. We actually do this in collaboration with our partners at Argonne and NERSC, because portability is important as well. So we don't want to do things that are exclusively for our system. We also want to help the others. And I'd like to get this book that we wrote together between the 3 sites. So these are the CAR projects that we selected 4 years ago. This is in a wide variety of scientific domains with different algorithmic features within their code, different programming models, different languages that they use to get as much experience out of this as possible. So we have climate science, we have relativistic chemistry, this is astrophysics, this is fusion energy, this is cosmology, this is linear scaling, electronic structure, this is biophysics, and the nuclear is nuclear physics, Chem is the traditional electronic structure in chemistry, QMCPAC is a material science code based on Monte Carlo, Raptor is a combustion code, so this is looking at combustion in complex geometries. SpecFam is a earth science application looking at the wave propagation within the Earth's crust related to earthquakes. And then NCHC is another fusion energy application. So what does it mean to be successful? Some projects use a figure of merit. They need to be X times faster between what they have now and what they have done. We decided we wanted to have a metric that only requires the machine itself. And so what we decided here is that they need to show on Summit, using CPUs and GPUs, reduce time to solution to beyond 20% of the machine. 20% of the machine is what we call the capability metric. This is what Insight uses in their application readiness review for their proposals. The second criterion is the performance. At 20% of the machine, you should get at least a factor of 2 in performance improvement from using the GPUs. So you do a CPU run only, and then you do a CPU plus GPU run, and you should get at least a factor of 2. That's not a high bar for a lot of applications, because there are only 10% or even less, 8% of the flops come from the CPUs. The rest comes from the GPUs. So there's an effect of 10 there. But some algorithms just don't lend themselves that well on the GPU. So that's why we say it's a factor of 2. So I have a few examples here. I don't know how I'm doing on time. Ganesh? How am I doing on time? How much time?
Yeah, we have time. We have.
Sorry?
3:24. 6. I mean, you can spend another 10 minutes.
Okay. I'll go through this quickly. This is GTC. So this is a fusion energy code looking at the plasma that burns within a tokamak. So this is for ITER. And GTC is primarily concerned with the stability of this plasma within this magnetic confined space. And so this is run on Summit with the GPU code up to a quarter of the machine, almost 1,000 nodes. And you see very good scalability. The CPU code scales perfectly up to that point, but they get a very significant speed up from using the GPUs. So they're done, check mark. NAMD, this is our biophysics code. So this is very similar to what Rob was talking about with the RAS-RAF protein simulations you would do with NAMD. This was led by Klaus Schulten, but he passed away during this project and taken over by Jim Phillips. So here's an example of Virion. So this is a billion atom simulation run on Summit. And again, this is the CPU plus GPU version, and this is the CPU version. And you see a significant speed up from using the GPUs. And you see still very decent scalability up to 1,024 nodes on Summit. So check mark number 2. This is nuclear physics. This code was really a research code when they started. And they had done everything wrong in that code for performance. All the data structures were exactly the opposite of what they should be. So nothing vectorized well. It was just, they need to do, I need help. No. Janessa.
I'm sorry. I don't know why this is popping up.
So they had to start basically from scratch. And so they have a very good scaling for the CPU code. You see it already starts to drop off dramatically for the GPU code. So they still get a factor of 4, and they still see reduced time to solution, but it's not. This was really a heroic effort, so we give them the check. QMCPAC. This was a code that already ran very, very well on Titan. This is a material science code, quantum Monte Carlo. Of course, it's Monte Carlo, so it scales really, really well. It's not that hard to do. But it's obvious in their coding. So this is the CPU runs, this is the GPU run. They get a speed up of 25. They are just able to, this has to do with the bandwidth. This is not the flop performance. This is, they did an excellent job in getting this to speed up on Summit. Raptor is this combustion code. This has a large number of components. So a large number of kernels that they needed to board. So this was quite an effort. Nevertheless, this is again GPU code, CPU code. You get a factor of 4, but they still have quite a bit scalability. So with some additional work, they may improve this still by looking at individual kernels. But this was really a whack-a-mole thing. This kernel is the worst performant, so let's work on it. And suddenly that's no longer the worst performing, and there's another one. So they had to do quite a few of those. So then the early science program. We did a call for proposals in December of last year, and we got tremendous response to that. I think actually so we got almost 50 proposals in June, and we just last week selected the ones that we go forward with on Summit. We had to wait so long because the machine was just not ready. And the amount of time that we have is for next year, the portion that goes to ALCC in July. And so we were hoping to have more time this year for the early science program, but that got smaller and smaller and smaller the longer it took for Summit to get accepted. So the number of projects will be relatively small. Then the Gordon Bell. So we had quite a few teams working on Summit for Gordon Bell, and eventually 5 of those became finalists. So if you go to the Gordon Bell session on Wednesday, you will have 3 talks, and on Thursday there are 3 more talks, and then somewhere mid-afternoon is the award ceremony, and the winner will be announced. So here are the finalists. Dan Jacobson with this genome-wide association study code. It's a bioinformatics code. That's the code that actually got 2.36 exa. No, they say exaops, but they're really floating point operations, so you should say exaflops, but it's only 16 bits. Then University of Tokyo team doing earthquake simulations on regional scale. So they did earthquake simulation that included the whole infrastructure. So they did a simulation on Tokyo Station with all the stores and malls underground and all the buildings around it, the high rises. And they have a lot of information about the structure of the subsurface. And so they looked at what building codes would be needed to withstand certain size earthquakes. And I'm a little bit torn. I'm on this project as a co-author, but it's not from Oak Ridge. So. Then Berkeley did a deep neural network to take climate simulations and identify within those simulations specific events. So when would you see a hurricane or something like that? Then an Oak Ridge team by Robert Patton did machine learning on electron microscopy data. So they have a large database of data to do machine learning on. And then finally a pure physics simulation by Andre Walker-Loud at LBNL to identify specific events that happen within nuclear physics. It's not my domain, so I won't say too much about it. So let me skip through this, because this is basically what I just talked about. Then, so this is the one that got the highest exaop rates on Summit with that bioinformatics, and they're very proud of this linear scaling with the number of nodes of this application. This is a project where I'm personally involved in. This is an electronic structure application in chemistry, where the team wants to look at organic photovoltaics and design these molecules in such a way that we get a higher yield out of photons that are being captured for photovoltaic devices. And this is again time to solution on the GPUs up to a quarter of the machine. And basically you see linear scaling here. And a factor of almost 7 if you compare at 1,000 codes the CPU-only version with the GPU version. So this is where you have to calculate millions to billions of matrix elements that in themselves are independent of each other. And so this can be very nicely load balanced using a task-based algorithm. So that's what we did. All right, then conclusions. There has been tremendous interest in using Summit from day one. When we did the call for proposals 4 years ago, we got quite a few more proposals than we anticipated. When we did this last year, for some additional projects to be added to this program in December, we had it open for a week and we didn't tell anyone. And we got 50 proposals. So there's a lot of interest in this. And a lot has to do with the tensor cores and how to do AI. Applications that ran very well on Titan tend to run very well on Summit. We just use what they, within Jaguar, call these resource sets, and you take a number of cores and you associate that with one GPU, and so you have 6 of these on the node, and you can basically treat them as single nodes, like what you would do on Titan. And so applications on Titan run very well on Summit as well. This is a multi-year effort, so we started with 13 projects 4 or 5 years ago. 5 of them have not yet demonstrated that they meet the scalability and performance metrics. So for some applications, this is really a heroic effort. So it's a multi-year process. Things that are really challenging with these systems is that the hardware and the software is constantly changing. So even when you are eventually working on the architecture itself, your software stack keeps changing on you all the time. And this is very, very frustrating to these teams. It's unavoidable, but it is very, very frustrating. Programming is more complex. We have 2 CPUs on the node, 6 GPUs. It's 1 memory space, but it has 2 NUMA domains. We have high bandwidth memory on the GPUs and slower memory on the CPUs. So this is complex if you want to really take advantage of the capabilities of this machine.
That's it.
Something that is really important, and I cannot stress that enough, is that to be successful, it really requires a partnership between the owners of the code who know the code itself and the method implemented, the folks at the centers who know their users and who know how we are going to use this machine, and then the vendors, because the vendors put this whole thing together, and so they know best the architecture. So it's really important to have those 3 work together within what we call centers of excellence.
I think you're missing a partnership here too. You have partnerships with universities that you probably don't really realize. We, in the field, doing the work at sysadmin level, are the ones supporting our users so that they can jump to your centers.
Right.
And I think you've forgotten about
Okay. Yeah.
the partnership that should be there with the universities.
Yeah.
Because we're kind of feeding you guys.
That's true. It's
Yeah.
true. In terms of the personnel that we need, that's absolutely true. Okay, so a lot of people have contributed to what I was talking about. This is not my work. And so this is our building. So Titan sits on the 1st floor in this part of the building. My office is right above it on the 3rd floor. This is the annex where on the 1st floor we have this concrete slab where our Summit currently sits. And if you want to come visit, you're very welcome to do so, but you have to let us know in advance because we have some procedures to go through in order to get on the site. But we really welcome you if you let us know in time.
Thanks.